So let's introduce the concept of friction. We know that if we have an object on some surface and we drag this object along, or if we launch this object of mass m on some horizontal surface, it will slow down. And the reason why it slows down is because there's a frictional force acting opposite the direction of motion of the object. So it has something to do with the surface. And a way to think about this is that if the surface will try to stop the motion of the object, you can sort of imagine that if you look closely, the surface has little spikes, and they sort of get in the way of the object, and they constitute a force that slows the object down. But if we pull the object off the surface, of course, the frictional force disappears. So it depends on how much we push the object down onto the surface. And a measure of this is actually the normal force, because if we do a free body diagram, then the force pushing the object down onto the surface is the gravitational force, but the surface reacts to that because it doesn't allow the object to fall through it. So we have motivated the idea that the frictional force, F, or little f, is equal to, or is proportional to the normal force. So it depends on how much the object is being pushed down, which then it gets reflected in the normal force. And it also depends on the kind of surface you have, and that's captured in some coefficient that doesn't have any dimensions. So we've motivated the frictional force as mu Fn, and we're not going to pay too much attention to the fact that if the object is sitting there at rest, there's the ability of the floor to sort of hold the object is different from when the object is moving, and so we can talk about coefficients of friction that are static or kinetic, but we won't really pay attention to that difference. Let's think about the frictional force on an inclined plane. Right, so here we will place the object on the inclined plane. The object has mass m. Let's say the angle here is theta. Well, we know that the frictional force has this form, so we need to know the normal force. And if we did a free body diagram, then we would have the normal force this way, right? Because it's not letting the object fall through the surface, but the surface is tilted this way. So the force that's normal to the surface is that way. And so to find the normal force, we need to find the force that's opposite, that's trying to pull it through the surface, if you will. And that's going to be, as we've seen before, the component of gravity. So it's mg cosine of theta. And again, we can figure out that it's the cosine of theta because as the angle goes to 0, the entire force of gravity ends up pulling it down because we end up in this situation. And so this has to become mg, and so it's the cosine of 0 that goes to 1, and so that works using that limit. So in this case, what we get is there's no acceleration in this tilted vertical direction, so we get 0 equals Fn minus mg cosine theta, and so on the inclined plane, we have Fn is equal to mg cosine theta, as we've seen, and the frictional force is therefore some coefficient of friction times mg cosine of theta.